All right, let's look at checkpoint number 8 here. So there's a survey conducted at Arizona State. So part A here is describe the experiment which may have resulted in this data. So what this experiment likely was is a survey which inquired what students basically racial background or ethnicity or however it was phrased, basically to report that information about themselves. So anything along those lines is probably a good indicator or a good description of where this came from. Part B, what is the sample space for this experiment? So the sample space, by definition, for an experiment is the list. Basically, it's a set of all the possible outcomes. So if I were to write out the sample space here, it would be, I would say S equals curly braces. And then what goes in these braces? Well, these are the outcomes: white, Hispanic or Latinx, Asian, 2 or more races, Black, African American, Native American or Indigenous, and Native Hawaiian Pacific Islander. So sample space, and one thing I want to point out is, like, in my experience, there's this urge or this temptation to kind of conflate a sample space with its cardinality. So what I mean by that is the sample space for this is not 1, 2, 3, 4, 5, 6, 7. The sample space for this is not 7. The cardinality of this sample space is 7, but the sample space itself is these 7 things: white, Hispanic, Latinx, Asian, so on. So that's the sample space. So if there were 120,000 students enrolled at ASU in 2021, how many were Asian American or Pacific Islanders? So those are 2 mutually exclusive, or we'll talk about that more later, why I think it's mutually exclusive. I'm going to treat them that way, though, is why these are 2 mutually exclusive outcomes from this experiment, or elements from the sample space. That's another equivalent way to say it. So since they're mutually exclusive, I'm going to use the addition principle, add those things together. So what's the probability of, can I call it double A? Yeah, I'll not. Probability that respondents were Asian is, I'll convert that percentage to a decimal, 0.0778. The probability that they are Pacific Islanders is, convert that to a percentage as well, it'll be 0.00189. So what's the probability of that somebody chosen at random was Asian or Pacific Islander? It'll be equal to the sum of those 2 things, which is 0.0778 plus 0.00189. So I get 0.0769. So that's the combined relative frequency of those 2 outcomes. So if I multiply that 0.0769 times 120,000, what do I get? Times 120,000. If I round to the nearest integer, I get 9,563. So by those probabilities, there must be very close to this number of students are either Asian American or Pacific Islander. Describe an event within the sample space whose relative frequency is at least 0.5, but less than 1. So lots of good answers here. I think the one that I will give is this. What if I make the event that a randomly chosen student from this survey is either white or Asian American? Because if I add those percentages together, I get 44.4 plus 7.78. That'll be approximately 52%. So That's what I wanted. I just wanted an event that was, had a higher probability than a half, but not certainty. So not quite one. But again, lots of good answers there. I just gave you one. E, are the elements in your sample space in this experiment mutually exclusive? And I'm going to say yes, but and I'll tell you that. But you could also, if you justify it right, I think you could say the answer is no as well. Clearly, it's possible to belong to, multiple categories. Maybe a student's racial background is white, Hispanic, and Asian. Then of course, these are not mutually exclusive because you can belong to all three of those groups. The reason I'm saying mutually exclusive because typically when these surveys are conducted, you're only allowed to choose one. So if that is indeed the way that this hypothetical survey is conducted, then they'd be mutually exclusive. But I'm willing to be lenient to this depending on how you kind of justify your answer, but I am treating them like they're mutually exclusive because I'm making an assumption about how the survey works. All right, moving on to question 2. All right, in an experiment, you're going to roll a 10-sided die and a 4-sided die and find their sum. So explain why the sample space has a cardinality less than 40. In fact, it's way less than 40. So why is that the case? Because it seems like, well, if I roll a 10-sided die, there are 10 options or 10 possible outcomes from that die, 4 possible outcomes from this die. These die are absolutely distinguishable. They don't even have the same number of sides. 10 times 4 is 40. But the sample space has to do with what the experiment is. In this experiment, I don't want to just write down what the individual numbers are. I need their sum. So what are the possible sums? Well, if this first die can have values from 1 to 10, and the second die can have values from 1 to 4, then what's the smallest sum I can have? The smallest sum I can have is 2. So, while I'm doing this, let me jump ahead to part B. What's the largest sum I can have? Well, if I roll a 10 on the first die and a 4 on the second die, that's going to be 10 plus 4, 14. So let me fill out a couple of these. 2, 3, 4, ... 12, 13, 14. So basically all the integers between 2 and 14, including 2 and 14, that's the sample space. So because my experiment is just basically, I'm going to roll them both, but I'm just going to catalog the sum. That's the sample space. It's not, for example, 1 and 1, 1 and 2, 1 and 3, and so on. So that's why the sample space has a cardinality of not 40. In this case, what is it? 2 to 14, that's 13 possible numbers. All right. But of those 13 possibilities, they're not equally likely to show up. So now I want to construct a relative frequency distribution for this experiment. This is the part where, even though the sample space does not consist of 40 elements, I still have to think about, the 40 possible outcomes because you've probably seen the videos or even dealt with this experiment in the past. Let's say you're rolling 2 typical dice, so 6-sided dice. The odds of you rolling a 7 are much different from the odds of you rolling a 3. Even though 7 and 3 are mutually exclusive outcomes, they're not equally likely to happen. So let's do this. Let's make a table here. Here's the 10-sided die. Here's the 4-sided die. So 1, 2, 3, 4. And I'll try to do this quickly because this is going to contain 40 cells in it, this table. So on the interior of this table, I'm going to write down the sums. So 2, 3, 4, 5, 6, and 8, 9, 10, 11. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So Now I want to make my relative frequency plot. So the relative frequency plot or the relative frequency diagram is going to have basically, I'm going to have one spot for every possible outcome. So my possible outcomes, we already identified the sample space: 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't budget my space well. That's okay. 1, 12, 13, 14. So those are my outcomes. What are the relative frequencies? So all of these are going to be out of 40. We might reduce them, but they're all going to be out of 40. What are the odds, or what's the relative frequency of 2? The only place 2 shows up is in this first, top left column. So the relative frequency is going to be 1 out of 40. Same idea for 14. There's only one possibility for that to happen. What about 3? So that'll be 2 out of 40. And we're going to kind of see this convergence from both sides. 13, there are only 2 possibilities as well. With 4, there are 3 possibilities. So 3/40. Similarly for 12. For 5, there are 4 possibilities. Let's do this. I'm going to assume this pattern holds. See what happens. Actually, that might be dangerous. It is dangerous because for 6, there are 4 possibilities. For 7, there are 4 possibilities. For 8, there are 4 possibilities. For 9 and for 10 as well. So maybe now that we've built this relative frequency plot, maybe we're nervous that it didn't work. How do I know this is right? So this is not like a perfect check, but one thing we can do, what do we know that when we add up all these relative frequencies, what do they really need to add up to? They really need to add up to 1. So I've kept them all with a denominator of 40. So the numerator should add up to 40. So 1 plus 2 is 3, plus 6 or plus 3 is 6. 10, 14, 18, 22, 26, 30, 34, 37, 39, 40. I feel good about that, at least, because all of the relative frequencies, accumulated together equals 1. So that's part C. So now I have these 4 events to talk about. For each of the following events, give a brief verbal description and its relative frequency. So E union F. So E is that the sum is even, and F is that the sum is at least 9. So E union F means that the sum is even or at least 9. So for part, Roman numeral I here, let's find the relative frequency of that. So to do that, let's pluck out the things in this chart or into this relative frequency diagram that actually fit E union F. So E is going to be met by 2, 4, 6, 8, 10, and 12. F is going to be met by the things that are at least 9. So 9, 11, 13, and 14. So that's most of my frequency diagram. So what I could do is add all these things together. What I'm going to do instead is this. I'm going to add all the things together that don't work. So 2/40 plus 4/40 plus 4/40. That is 10 out of 40, which means the probability of being inside the things that I have check marked is going to be 1 minus 10 over 40. That'll be 30 over 40 or 3 over 4 or 0.75, however you'd like to say that. All right, let's go ahead and clean up and answer the next one. G and H complement. So what does G mean? G means the sum is at most 5, so 5 or less. And then H means it's a multiple of 3. So H complement means it's not a multiple of 3. So I need the sums that are 5 or less and not a multiple of 3. So 5 or less is 2, 3, 4, or 5, right? But I only want the things in there that are not multiples of 3. So 2 is less than 5. Is it a multiple of 3? No. So this is okay. 3 is less than 5. Is it a multiple of 3? It is. So I'm going to ignore it. 4 and 5 are, I shouldn't say less than 5. I should say at most 5. But also not multiples of 3. So I like those. But now I'm going to add those together. 1 plus 3 plus 4. Our relative frequency there is going to be 8 out of 40, or if you want to reduce, 1/5 or 0.2. All right. Finally, let's clean this up one more time. Okay. So I got 3 different sets to worry about. Let's do them, from parentheses outward. So where is E? E is that the sum is even. I want the complement of that, which means essentially the sum is odd. So I want odd sums, or where the multiple is 3. So I'm going to do this. Where is the sum odd or a multiple of 3? So odd is 3, 5, 7, 9, 11, 13. Or a multiple of 3. So what else do I have to add? 6 and 12, right? Okay, so those check marks, some of those are going to go away because, so those check marks indicate what belong to E complement union H. But now I have to get rid of the ones that don't belong to F. So F is the ones that are, F is the set of sums that are at least 9. So I have to get rid of 3, 5, 6, and 7 because those are not at least 9. So basically, I have whittled this set notation down to my event space of 9, 11, 12, and 13. So what are the relative frequencies there? 4 plus 4 plus 3 plus 2 all over 40. So that's 8, 11, 13. So relative frequency here is 13 over 40, which I don't believe reduces at all, but what if I want to give you a decimal? 13 divided by 40 is 0.325. All right, so that's all for checkpoint number 8.